Ladies and gentlemen, let's continue with chapter 4, Transient Heat Conduction. The chapter in principle has four major parts. The first one is the lump system, a very, very simple equation, but the limitation of that equation is that you cannot determine the temperature at different positions in a body. The temperature that you work out is the temperature everywhere in the body. Why? Because the internal resistance is much, much smaller than the external resistance. That ratio is, if it's less than 1 to 10, which is the Biot number, then usually it is a good rule of thumb to say that we can use the lump system approach. Right, paragraph 4.2 was then on long cylinders, plane walls, long plane walls, and spheres. Why the long and the long? To limit our problems to one-dimensional heat transfer. We've started with the one-dimensional energy, with the energy equation. We did all the calculations. We reduced it to a relatively simple partial differential equation. The problem with that approach is that if you want to determine something, it depends on 8 other things. So other researchers were very clever and they reduced it to one variable depending on 3 others. But in a non-dimensionalized form, it was possible for them to solve it, and the solution is typically table 4.1 in the textbook of Cengel that we've already discussed. Okay. Now, in terms of the applications of these equations, we already did an example, and now we are busy with another one, which is problem 590. Problem 459 at the back of the textbook of Cengel and Ghajar. And this problem is about a beef carcass of 65 kilograms. The K value and alpha is given initially at a temperature of 37 degrees Celsius to be cooled by refrigerated air at minus 10 degrees Celsius, flowing at a velocity of 1.2 meters per second. The average heat transfer coefficient 22 is given. Now, treating the carcass as a cylinder with a diameter of 24 centimeters, 240 millimeters, and a height of 1.4 meters, and disregarding the heat transfer from the base and the top surfaces, determine how long it will take for the center temperature of the carcass to drop to 4 degrees Celsius. And also determine if any part of the carcass will freeze during the process. And then I've added a few more questions to this problem, and that is to determine the amount of heat transfer, which is in joules, then the average heat transfer rate, how many watts over the period, and then how much will it cost if the electricity tariff is 2 Rand per kilowatt hour, and I think I've set a COP value of the vapor compression and refrigeration system of typically about 2. So that was a problem, and with the previous lecture we've already started with it. We've done it in much more detail. We've looked at this equation for a cylinder, which is an infinite series. We've realized that if we make the assumption that tau is larger than 0.2, the error would be less than 2%. And we've calculated Biot number, and with that, in the tables, we could get the roots and the A1 value. Okay, take note, it is only for n equal 1. And if you cannot make that assumption, then you will have to go and calculate the other values yourselves. You can do it numerically. Okay, we've done that, and we have also looked at the equation and said, but we can actually simplify the equation a lot, because we want to know the temperature at the center. And at the center, R is equal to 0. And the result of all that is that this complicated equation, if we can only use n equal 1, can be reduced to this very simple value. We've calculated the tau, which is about 0.4, so it looks fine, and it says that we can use this approximation. If tau was maybe far less than 0.2, then it means you will have to go and calculate also the other roots and the a values for n equal 2, 3, etc. to get the thing to be more accurate. And from that, we've determined the time would be about 12.2 hours. So it will be 12.2 hours before this carcass, which is at 37 degrees Celsius, outside temperature minus 10, will be cooled so that the center temperature is 4 degrees Celsius. Right, so that's the first part of the question. Let's do the rest. Okay. Now the rest is, the next part is, will any part of the body freeze? Okay. So there's no one single equation that we can use for that. We can use our judgment in terms of where we will think will the lowest temperature be. What would you say? Where will the lowest temperature be? It would be on the surface, isn't it? Because this temperature is minus 10. On that side it was 37. So this is exposed to the lowest temperature. So that would be most probably the place where the temperature would be at its lowest. If you are not sure, you can go and calculate it at quite a few places and make sure. Okay. So let's say we are going to check it where R divided by R0 is equal to 1. Okay. Okay, remember, if that is the cylinder, and that would be R, okay, and that would be R0. So, at this point, R divided by R0 is, of course, R0 divided by R0 is 1, both 240 millimeter. Okay. So, with the previous lecture, somewhere here, I've indicated this equation as equation number 1. Okay, so I'm referring to that equation. Okay, so in terms of equation 1, we can then say theta is equal to A1 e to the minus lambda 1 square multiplied by tau multiplied by J0 multiplied by lambda 1 multiplied by R divided by R0. Okay. And R divided by R0 is equal to 1. Okay. So the equation now becomes theta is equal to A1 e to the minus lambda 1 square tau multiplied by J0 at lambda 1. Okay. Okay, and this temperature in terms of the definition is the temperature minus T infinite divided by Ti minus T infinite is equal to all those terms. And this is now the center, the center, sorry. Not the center temperature, the temperature at R0 as a function of time. Okay. Temperature R0. Now, depending which nomenclature you want to use, I've used it like this, the temperature at R0, okay? Minus T infinite divided by Ti minus T infinite is equal to still everything on the right-hand side. Now, in terms of this term, J0 in lambda 1 that we need. That would be J0 in the point, at the point 2.027. Okay. And sometimes it's very confusing to students, but that is eta. In terms of the nomenclature that is used in the table. Okay, so eta is everything in the bracket, or that term everything in the bracket. Okay, in this case, the ratio of the radii is 1. Okay. So if we now look at this table for a J value of 2.027, what would it be equal to? (2.020), the J0 value, there it is. It would be somewhere between 0.2239 and 0.1666. Do you agree? Everybody happy with that? Okay. Now I've calculated it, and it is equal to 0.2083. Okay, now ladies and gentlemen, you have to be very, very careful now. These Bessel functions of J0 and J1. Last week, Thursday, I've sent you a link through that you can use for the calculation of these values. Okay. If you go and check, you will see that some of these values here are incorrect. Okay. Typically about the values here. Okay, and I think those are all positive values. Okay. So please go and correct it. Okay. You don't look sure. Okay. So the values there, something went wrong with the calculation of it, and they are not correct. When I looked quickly, it looked to me as if it's typically the values larger than 2, and specifically the J1 values. Okay, so please just go and check them and make sure they are correct. Okay, right. So now, in terms of this equation, and I'm just going to write it down so that you can see what we are calculating. The temperature at R0. Okay, so we're calculating the temperature there. Minus T infinite divided by Ti minus T infinite is equal to A1e to the minus lambda 1 square multiplied by tau multiplied by J0 in lambda 1. Okay, so this is J0. Okay. The temperature on the outside is what we want to determine. Okay, minus 10, 37 minus 10, okay, is equal to A1, which is equal to 1.517, e to the minus lambda, which is 2.027 squared, multiplied by tau, multiplied by 0.2083. Okay, sorry, I've made a mistake. Obviously, we want to calculate tau now at this value, at 12.2 hours. 0.396. Otherwise, we have two unknowns, the temperature on the outside and tau. Okay. Okay, so this temperature that we now calculate is equal to minus 7.1 degrees Celsius. Okay, minus 7.1. Okay. Does it make sense? Okay. Always remember when you do calculations, ask yourself, does it make sense? Okay. What would be a sanity check in this case? What would be sanity checks? It's very easy to make errors in calculations, and especially in the test and the exam. Okay. Now maybe you can get 1 or 2 more marks if you've made an error, but at least you recognize it and you can tell me why. Okay. So let's suppose you've calculated minus 15 degrees Celsius. Would that make sense in terms of this problem? Minus 10 on the outside, a body with 37, it wouldn't make sense. You agree? Or if this temperature would be more than 4 degrees Celsius, okay, more than the temperature here in the center, it also wouldn't make sense. Okay, so always ask yourself, does it make sense? So minus 7 degrees is in between minus 10 and the temperature here, which is now 4 degrees Celsius. So with part A of this problem, we've determined how long it will take for that temperature to be 4 degrees Celsius if it's minus 10 here. And that was after 43,865 seconds or 12.2 hours. Okay. So this problem tells us now that after 12.2 hours, this temperature here is minus 7 degrees Celsius, and yes, freezing will occur in this case. Okay. Okay. So the conclusion that can be made is the outer part of the carcass will freeze, which is not good. Okay. So the design of this refrigeration system needs to be changed. Maybe the velocity is too high, or the temperature might be too low. Okay. Right. Are you with me? Any questions, ladies and gentlemen? Right. Now, the third part is to determine how much heat is being transferred. And take note, in the question I've said how much heat. I did not say the heat transfer rate. Okay. So the heat which is transferred. Okay, and heat is joules, which is now being removed from the carcass. Okay. So again, let's just look at these graphs because they really help me a lot when I have to look at this stuff. In the sense that, firstly, I'm somebody that's normally interested in the heat transfer rate, in the watts, and not so much in terms of the amount of heat transfer, which is in joules, as a function of time. Okay. So at T equals 0, in both cases, up to 12.2 hours. T equals 0, up to 12.2 hours. With this problem, typically the heat transfer rate is going to do that. Why? Because the temperature of the body is decreasing. Okay. So the rate at which it can transfer the heat is just getting lower and lower as the body temperature decreases. When the body was at 37 degrees Celsius, the heat transfer rate was at its maximum. And with time, it starts going lower and lower and lower, up to the point where everything on the inside is at minus 10. Then there can be no more heat transfer rate occurring. Okay, so that would be typically when the initial temperature was 37. It would decrease, and that would be where the center temperature is at 4 degrees Celsius. So that is typically what will happen with the heat transfer rate. The heat transfer, the amount of heat transfer is going to, it's going to do something like that, okay. Because it's being cooled, so heat is being removed out of the body, okay. Heat is not being added. You agree? The heat in the body, there will be a certain number of joules in terms of the energy because of the temperature, and it decreases as it is being removed out of the body. So again, that would be at 37 and that would be at 4 degrees Celsius. Yep, question?
Isn't the graph like that?
No, in other cases it was like that when you did heating, because then you're adding the joules. In this case, you're removing the joules. Okay, that's the difference.
So that's below the zero axis.
Yeah, well, it depends now, how you want to define the zero. Or how do you want to define how much energy the body had at the beginning. Okay, so if we start at any arbitrary value, we know it's going to get less because the joules are going out of the body. It's not coming in this case. Okay. Okay, so what we have is obviously the body at Ti, which was 37, and that is at infinite, which is at -10. That was at the beginning what happens. So let's on the left-hand side write down the equations for the heat transfer rate, and on the right-hand side the equations for the amount. Okay. Now in terms of the heat transfer rate, okay, Q dot, the heat transfer rate. Okay. Okay, let me write it like this. HT for heat transfer rate. And the units will be in watts. Okay, now the first thing that we can say is the maximum heat transfer rate, okay, would be m dot Cp multiplied by Ti minus T infinite. Okay. The m dot would be the mass divided by delta T. So in the beginning, if delta T is very small, then we will have the maximum heat transfer rate. Because at that stage, the temperature difference is at its highest, 37 and -10 degrees. Okay, that would be the maximum. Now, at any specific time, ladies and gentlemen, can you see if I write here, any specific time? Okay. I will in any case say what I'm writing. So at any specific time, the heat transfer rate, which is Q dot, is now equal to M divided by T minus T, and it depends which T you want to use now. Any one of the two you can define as T equals 0, and that would then be Ti minus the temperature as a function of T. Okay. So at any specific time, if the temperature is going to decrease, so at this time we need that temperature, which is now going to be less than 37, and that is going to be the heat transfer rate. So the heat transfer rate is not a constant, it starts going down. Okay. While on this side, we have Q, which is, let's call it the heat transfer amount. Okay? And this will be in joules. So this one would be the rate, and this one would be the amount of joules. What would be the maximum that can be transferred? The maximum would be equal to mCp Ti minus T infinite, which means it is everything. Okay. From 37 to the body going down to minus 10. So that would be the total that can be transferred. Or at any specific time, Q would be equal to M multiplied by Ti minus the temperature as function of time. Am I confusing you? Yep.
CP, Mr. CP.
Ah, sorry. Okay, thank you. Okay. Oh, sorry, you also. I've got my CPs. There you go. Okay. Okay. Now again, it might look a little bit confusing, but let's start making it a little bit more practical. Then you'll understand why I did it and what I've tried to show you. So let's first go and calculate Qmax. Qmax, the amount of heat transfer, which would be mCp multiplied by Ti minus T infinite. Okay. What does this equation mean? It means this Carcass is at 37 degrees Celsius at T equals 0, and then at T equal a time longer than 12.2 hours, because at 12.2 hours this temperature, let me do it rather like this. Let me do it like this. Let's say this is at 12.2 hours. That will make it more clear. Then at 12.2 hours, that temperature there is 4. Okay. This temperature there is minus 7.1. So the question is, can more heat be removed out of this body? Of course, because it is not at T infinite. That is what we want to say or determine. So at T equal infinite, or not infinite, but at a long enough time. So I'm going to say it like that, okay, a long time. Okay. You can get this body so that that temperature is minus 10, that temperature is minus 10, the outside temperature also minus 10, and every temperature on the inside is minus 10. Okay. And that would be Qmax. Okay. So Qmax would be how much heat is needed to take this body of 37, the whole 65 kilograms, and everything is being cooled down to minus 10 degrees Celsius. Right. So in terms of that equation now, so Qmax is equal to the mass, which is 65, Cp, which is 4180, and the temperature initially at 37, which is now being cooled to minus 10. Okay. And that would be 12.77 megajoules. Okay. So to get to this point where everything is at minus 10 would be 12.77 megajoules. That's not a calculation for that. It's for this one. Okay. So, if you now want to get how much heat is being removed to this body, then you just have to go back to the calculations. We've done the derivation of it. Okay. And the result of that is that for a cylinder, it can be written as Q divided by Qmax is equal to 1 minus 2 times the non-dimensionalized temperature at the center of the cylinder multiplied by J1 in lambda 1 and divided by lambda 1. Okay. And we can calculate it now. So Q divided by Qmax. Qmax we've calculated just now. 12.77 megajoules is equal to 1 minus 2 times the non-dimensionalized temperature, okay, of the cylinder. Now, that would be equal to that calculation there. So that term, let me just write it. Sorry, not this term. This one here. Okay. So that term there is the non-dimensionalized temperature. Okay. With the previous lecture, I think we've written it down. Okay. Just to make sure, let's just write it down. So the non-dimensionalized temperature of the cylinder is equal to T0 minus T infinite divided by Ti minus T infinite. The temperature at 0, the temperature at the center, T0, is 4, minus the temperature on the outside, which is minus 10, divided by the initial temperature, which is 37, minus 10 again. And that is equal to 0.2978. Okay. So that is where that comes from. So 0.2978, okay, multiplied by J1 in lambda. And lambda is equal to 2.027 divided by lambda, which is equal to 2.027. Right? So if we look now at J1, what is the value of J1 equal to? At 2.027, okay? You can see it should be between 0.5767 and 0.5683. Okay, you agree? Okay. So you will see that the values there starts becoming inaccurate. If you do the calculation, then this value is equal to 0.5748. Okay. And that then comes from table 4.3. Okay. So the only unknown is the Q. And Q is equal to 10.12 megajoules. Again, the sanity check. If that value would be more than 12, you know, 12.77, you know something is wrong. Okay. So Q would be 10.12 megajoules. Okay. And that's the third part of the question. Okay, while I'm cleaning the board, take a good look at it before we continue. Any questions, ladies and gentlemen? Yep, here's a question.
Sorry, sir. Back to that graph of the heat transfer. If you look at our results now, it increases the heat transfer. That graph, isn't that graph the heat in the body?
Yeah, sorry, you're right. Let me see. Yeah, okay. So, all right, okay. So that is the heat in the body. That's that, you're right. Okay. So the heat in the body is decreasing. So let's produce a third graph, which we can say the heat transfer out of the body. Okay, let's do it like that. Q out in terms of joules right, in terms of time. Okay. So if we assume a t equals 0, and that is 12.2 hours, and that would be infinite. So if we would assume in the beginning it is 0, then after 12.2 hours, then that would be 10.12 megajoules, which is being removed, and then it will get to that point after which the curve is flat, which is equal to 12.77 megajoules. Okay. So yes, so just make sure in terms of the heat of going out of the body or the heat of the body. Okay. Any more questions? Yep.
So I'm just a bit confused with the Q over Qmax equation. How did we get there?
Okay, we don't have time to do the derivation now, but it comes from the derivations of this term where where you've got Q. Okay, so you can calculate Q, and if you've got Q, the temperature distribution, then you've got the temperature gradient, and therefore you can calculate the heat transfer rate on the surface or anywhere else. So in the textbook, the derivation is given, and there are 3 of them. So there are 3 equations, the one for the plane wall, the one for the cylinder, and one for the sphere. Okay. And it is not that complicated just to derive them very quickly. But they are in the textbook. Okay. Any other questions, ladies and gentlemen? Right. The next part of the problem was now determine the average heat transfer rate. Okay. And why do I say average? Because as we can see in the beginning, it's going to be very high, and then it is going to get lower. Okay. So the average would be something like that we would be interested in. Okay. Okay, so let's look at part, is it part D? The average heat transfer rate to be determined. Okay, now the amount of heat transfer or heat, let's rather say it like that. The amount of heat that was removed that is the question. The amount of heat that was removed, or that is being removed. Let's start like that. The average heat transfer rate, the average, okay, would be the amount divided by delta T. Okay. So in terms of our graph, the heat transfer rate as a function of time does something like that, up to 12.2 hours. Okay. The average, there's more than one way that we can do it. We can go and calculate the Q per second. For each one, calculate that, do the integration, or we can just say, it is sort of the average under the curve, which is a good engineering approach, which means the total, which is that amount, 10.12 joules, divided by delta T, which is 12.2 hours or 43.865 seconds. And that would then be 231 watts of heat on average that is being removed. It's quite an important thing for anybody to know in the air conditioning and refrigeration industry, because if you do the sizing now of your equipment, you need to know for what you must design, or if you want to buy it, how large the unit should be. So, now that you know that, will you buy this unit, a unit which is on the market for 231 watts? Would that do the job for you? Why not? Why will it not do the job for you? Because at the beginning you need much more. You need to remove much more. Okay. So this unit is not going to do it if it can only do 231 watts continuously. At the beginning you need much more, but that would be the average. Okay. So let's go and calculate the heat transfer rate at T equals 0. What would the heat transfer rate be at T equals 0 when you just put it on? The heat transfer rate would be this equation. Do you agree? Okay. But delta T is 0. So do you see what happens with this equation of yours? Okay. Obviously, you can say, well, that gives me problems, but I'm not really interested in what happens in the first milliseconds. I'll be happy with the first minute or so, and then you can do the calculation like that. But sometimes we forget there's an easier way of calculating it, and that is just by using the convection heat transfer equation. Okay. We can say at T equals 0, the heat transfer rate would be equal to the heat transfer coefficient multiplied by the area multiplied by the initial temperature of the body on the surface, which is 37, minus T infinite. Okay, the heat transfer coefficient of the body is 22. The surface area is pi multiplied by the diameter, which is equal to 0.240, okay, multiplied by the length, which is 1.4. Okay. Now remember, we are now only looking at this surface here on the outside. Okay. Because in the problem they told us we can ignore the heat transfer from there. In this case, maybe you can add it if you want to, if you really want to determine the maximum, because obviously there's going to be heat transfer from there also. So you can put it in. Okay. Multiplied by 37 minus 10, and that gives us 1091 watts. So, again, to summarize this problem, if we look at the heat transfer rate in terms of watts, okay, that value there is 1091. That would be T equals 0. That would be 12.2 hours. Okay. And what will happen now is that the temperature would decrease in the center to 4 degrees up to that point there, and 231 would be that average there. The average is 231 watts. And what we can also do is we can actually now calculate what is the heat transfer rate at that point there also, because we have the temperature on the surface. Okay, so the heat transfer rate, or Q, at 43,865 seconds, okay, after 12.2 hours, then the heat transfer rate be equal to the heat transfer coefficient multiplied by the area. But now, again, those two values are still the same. Okay, 22 multiplied by pi, multiplied by the diameter, multiplied by the area. But now, what is the temperature on the surface? It is -7, because that is the heat transfer rate of convection to the environment, minus 7.1. Okay, minus 10, and if you calculate it, then that would be 69.67 watts. So, that heat transfer right there would be 69.67, and that would be the average of 231 watts. You understand? Okay, the kilowatt hours being used. Okay, the kilowatt hours of heat which is being removed is equal to this average of 0.231, which is in kilowatts, 0.231, multiplied by the time in hours, it's 12.2 hours. Okay. So the kilowatt hours which is being removed out of the body is 2.086 kilowatt hours, which is removed. Okay, now I don't know if you can still remember the thermodynamic cycle for the vapor compression system. It has a compressor. Okay, the heat of the condenser, QH, and that is QL, the heat transfer rate to the evaporator. And the COP, the coefficient of performance, would be the amount of heat transfer, which is QL, divided by the energy we pay, which is that for the compressor, which I've said is equal to 2. Okay. So it means for every 2.806 kilowatt hours of heat being removed there, I only use half of it to drive the compressor. And that is where I'm going to pay my electricity. Okay. So the COP, which is equal to 2, QL divided by the compressor, that is 2, and that is equal to 2.0806 in terms of kilowatt hours. Okay, the work of the compressor also in kilowatt hours, and that would then give us the work of the compressor in kilowatt hours would be 1.403 kilowatt hours of electricity being used by the compressor. All right, and the cost at 2 rand or $2 per kilowatt hour, whichever the electricity rate in your country is 1.403 multiplied by 2, and that would be 2.80 rand in doing the job for us. Any questions, ladies and gentlemen? Okay. Now what I want you to do for the next lecture is I want you to go and do the same problem but using the Heisler charts. Okay, so go and do the same problem with the Heisler charts, and then we will see how it goes. Thank you very much.